Welcome to the graphing functions unit. The first thing we're going to work on is finding the max and min values of a function given an interval. Let's go over some definitions to begin with. We say that f of x has an absolute or global maximum at x equals c if f of x is less than or equal to f of c for every x in the domain that we're working on. This means that the y values of the function are less than or equal to the y value at x equals c. So this means that f of c is the maximum value of the function. Okay, next up, we say that f of x has a local or relative maximum at x equals c if f of x is less than or equal to f of c for every x in some open interval around x equals c. Sorry about that typo. I'm just going to get rid of that. So when we talk about an open interval around x equals c, we mean that we can find some interval a, b, not including these endpoints. So c is contained between a and b, or in other words, it's not going to be either of these endpoints, A or B. Okay, so it has to be somewhere in between. So just keep that in mind. That's what we mean by open interval. Okay, a couple more definitions. We say that f of x has an absolute or global minimum at x equals c if the y values of the function are greater than or equal to the specific y value at x equals c. Okay. So this means that f of c would be the minimum value of the function. And then the last definition, we say that f of x has a local or relative minimum at x equals c if the y values are greater than or equal to the y value at x equals c for every x in some, again, open interval around x equals c. And one more time, open interval means that c is between endpoints a and b, and c cannot be a or b. So, which really means that we can't have any local or relative maxes or mins at the endpoints. And we'll see on the next page what this looks like. So we will collectively call the min and max points of a function the extrema of the function. The vocabulary for this unit. We will call the relative minimums and maximums the relative extrema, and the absolute minimums and maximums the absolute extrema. The bottom of this page just sort of recaps what we've just discussed. So one more time to recap, we have absolute maximums, which was condition one that we discussed, or absolute minimums at x equals c, provided that f of c is the largest or smallest value that the function will ever take on the domain that we're working on. Okay, for a point to be a relative maximum or minimum, it has to be a max or min in some interval of x's around x equals c. So there could be larger or smaller values of a function at some other place along the function, but close to or local to x equals c, f of c is larger or smaller than all of the other function values that are near it. Okay, and just one more time, we're going to be using the definition of relative extrema to be the ones that do not occur at the endpoints of a domain. So that just relates back to what I wrote up here. So that means that in order for a point to be a relative extrema, you have to be able to look at a function values on both sides of x equals c to see if it's really the max or min at that point. Okay, let's move on to the next page. So at the top of page 2, for this graph of a function given, you can see where all of these extrema points lie. So we have an absolute maximum at x equals d, but we would also consider this point to be a relative maximum because right in this interval around x equals d, it's the highest point. Okay, so it fulfills both conditions 1 and 3. This lowest point of the function here, that would be considered the absolute minimum. Oh, sorry, I think I mixed up my colors. I'm just going to fix this up. Sorry, this should be 2 and light blue for relative maximum. Okay, so here we go, absolute minimum at point x equals a because it is the lowest point on this entire function. So that would be condition number 3. And then you can see that we have other points here. This is the relative maximum as well, because right in this open interval around x equals b, the y value is at its highest. And then we have this point at x equals c, which is the relative minimum, because again, at around this interval where x equals c is located, this y value is the lowest possible. If you notice, we only have one absolute maximum and one absolute minimum in this function, but we can have several relative extrema. So you can see we have 2 points here that would both be considered relative extrema, and we have one relative min here. Now, some of you might be wondering why this point hasn't been labeled. Remember that this is not an absolute minimum because we already see that this point at x equals a is lower. And it can't be the relative minimum either, because we said in the previous page on the definitions that we can't have a relative minimum at an endpoint. And the same reasoning goes for this value here. So this is the absolute minimum, but it is not the relative minimum because it is an endpoint. Looking at the next example, we're trying to figure out the absolute extrema and relative extrema for the function f of x equals x squared on this closed interval between -1 and 2. So when we take a look at the closed interval, we can see that we have this point here, which we would consider to be an absolute and a relative minimum point. We also have this point up here, which would be considered to be an absolute maximum point. However, it is not considered a relative maximum. It's because it's an endpoint. And remember, we said no relative extrema at endpoints. And last but not least, this point here, again, it would not be considered an absolute max or an absolute min. We already have one of those. And it can't be a relative maximum because it is an endpoint. Okay, let's work on example 2. I'm just going to slide up the page. So now let's think about identifying the absolute and relative extrema for the function f of x equals x squared. And this time I haven't given you a closed interval. So this means that I'm saying the domain is just x belongs to a set of real numbers. So let's think about what this function looks like. Just a quick sketch here. So this is my f of x equals x squared. My domain is x belongs to the set of real numbers. And my range is that y has to be greater than or equal to 0. So in this case, the only relative or global extrema that I have is at the vertex. And that would be my absolute minimum right here. Okay, which would also be considered a relative minimum. But in terms of other extrema, so there's no absolute maxes and there are no local maxes either. So sometimes an answer can change depending on whether you are given a closed interval or a completely open interval. Okay, let's move on to page 3. In example 3, we have a cubic function on this closed interval between -2 and +2. So just by looking at the graph, we can see that we are going to have an absolute maximum at this point 2, 8. And then we are going to have an absolute minimum at this point, -2, -8. And in spite of the fact that we can see these points are at the highest and the lowest values, these would not be considered relative extrema because they are endpoints. And again, when we take a look at this function without the closed interval, so it's the same graph, but this time I can put arrows on the end to show that the graph just continues in both directions. This means that now, all of a sudden, we have no relative or absolute extrema. And this happens because the domain and range are both y belong to the set, or x and y belong to the set of real numbers. Not that this is the only way that you can identify no relative or absolute extrema, because if this is the case, sometimes you might have, let's say, a cubic function that kind of looks like so. So in that case, you would be able to find some local maxes and mins. Okay. I'm going to slide up the page for example 5. And here's one such case where the domain will be XER, but we will still have some maxes and mins. So the absolute and relative extrema for f of x equals cos x. So we can see that these points here, 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 they would be considered the absolute maximum of the function, and at the same time, they would be considered the relative maximums as well, okay, because they're all within open intervals. we have an absolute maximum value of 1 at x equals negative 2 pi, 0, 2 pi, and etc. on both ends. So we're going to write this as we're going to write this as x equals 2 pi n. N belongs to the set of integers, so meaning multiples of 2 pi, essentially. Okay. And this is also relative maximums. And then at these points down here, we are going to have our absolute minimums. So our absolute minimums of negative 1 at x equals negative 3 pi, negative pi, pi, 3 pi, etc. So again, in general equation form, we're going to write this as x equals pi plus 2 pi n. N belongs to the set of integers. So you start off with pi, and then you add multiples of 2 pi to get these x coordinates. And again, this is not only absolute minimums, but they would also be considered relative minimums. Let's move on to page 3. Oh, sorry, let's move on to page 4. Just to summarize the results of the examples that we went over on pages 2 and 3, all of those functions that we considered were continuous functions, no gaps or breaks in the graph. And every time we had an example where the domain was restricted to a closed interval, so meaning that we contained the endpoints in the interval, we ended up being able to find absolute extrema. In only one of the 3 examples where we did not restrict the domain, we actually did find an absolute max and an absolute min. And that only happened for the example with f of x equals cos x. So f of x equals cos x was sort of a special exception. So otherwise, we need to really check to see if these 2 conditions are met in order to use something called the extreme value theorem. So extreme value theorem says, suppose that f of x is continuous on this closed interval where x is between a and b and can include a and b. So then there have to be 2 numbers where a is less than or equal to c and d is less than or equal to b, so that f of c is an absolute maximum for the function and f of d is an absolute minimum for the function. Okay, so basically just another way of saying that if we have a continuous function on a closed interval, we must have absolute extrema. And these absolute extrema could just be the endpoints. And in fact, that's a good point to start at. So let's go over this example. So consider the absolute extrema of f of x equals 1 over x squared. It's a rational function. And we're given this closed interval between negative 1 and positive 1. So as you can see, we have an absolute minimum at x equals negative 1 and at x equals 1. Those are our absolute minimums. And because the function really continues towards this vertical asymptote at x equals 0, there would not be an absolute maximum. So it actually turns out that in this example, the extreme value theorem doesn't work. And the reason why is because, if you notice, f of x is not continuous on this closed interval. EVT, extreme value theorem. So because the function is not continuous on the closed interval that we were given, extreme value theorem will not necessarily hold true. But now let's repeat this exercise given the closed interval half to 1. So in this case, we'll have this value 4 up here and this value, oops, sorry, 1 over here. So just on the interval from half to 1, the function will look like this. Okay? And in which case, it is continuous on this closed interval. Okay? So the way that I figured out those values, f of half is 1 over half squared, which is 1 over a quarter, which is 4. F of 1 is 1 over 1 squared, which is really 1 over 1, which is 1. So we do have a closed interval, and we know that f of x is continuous on the closed interval that we're given. So that means that extreme value theorem will hold. And we have to have an absolute maximum and an absolute minimum. And we can see that the absolute maximum is going to be at x equals half right here. And we'll have our absolute minimum at x equals 1, which happens to be the endpoints, which is fine because we're not talking about relative extrema. Relative extrema not allowed to be at endpoints, but absolute extrema can certainly be at endpoints. So just to summarize what we figured out earlier, for example, 6a, as long as the interval does not contain the point of its discontinuity, the extreme value theorem will hold. Okay, let's move on to page 5. Just to go over an example of a function that is not continuous, but still has absolute maxes or mins. That's what the top of page 5, this graph of the function, is giving an example of. Okay, so you can see that we do have, in this case, an absolute maximum at x equals b. As well as an absolute minimum at x equals c, even though the graph has a break at x equals c. Okay, so in this case, I'm showing you a graph that has an absolute extrema at the point of discontinuity, but it doesn't always need to. Okay, the absolute minimum could have been at the other endpoint or at some other point that's contained within the function. Okay, so basically, we need to be careful to only use extreme value theorem when the conditions of the theorem are met, but not misinterpret the results if the conditions aren't met. So what I mean by that is just because a function is continuous, or discontinuous rather, does not mean that it won't have absolute extrema. So just keep that in mind. So in this next part of the lesson, we're going to look at how derivatives can help us figure out where these absolute maxes, mins, relative maxes and mins are located. Because in the examples that we gave you before, they were relatively easy to graph, but not every function is going to be like that, right? So we want to try to use some algebraic methods to figure out where our relative and absolute extrema will lie on the function. So Fermat's theorem says, if f of x has a relative extrema at x equals c, and f prime of c exists, meaning that the derivative at x equals c exists, then x equals c is what we call a critical point of f of x. And in fact, it's going to be a critical point such that the derivative f prime of c will equal 0, which means that, as you probably have figured out, relative extrema should have tangent line slopes of 0, which is what the derivative really means, right? It's the tangent line slope. And if you think about what relative minimums and maximums are, they're the points at which the function changes from an increasing to a decreasing function. So all of a sudden, the tangent slopes go from positive to negative or from negative to positive. So at those points, the slope should be 0. Now, a couple of notes about Fermat's theorem. Just note that critical points not only exist where the derivative exists, but they can also exist where excuse me, f prime of c does not exist. So, for example, if you have a little, just give me a little sketch of a function that has a corner point. Okay? So in an absolute value function, for example, this would be considered a minimum point, in fact, an absolute and a relative minimum, even though f prime of c does not exist. Okay? And another example would be a function that has a cusp point. Again, an absolute minimum, even though the derivative does not exist at the corner or cusp points. Okay? But that doesn't always necessarily mean that every f prime of c does not exist will lead to a critical point. As you can see in this example, for an infinite slope point, the derivative will not exist at this value of x equals c, but it's not considered to be a critical point. You can see that it's not a relative maximum or minimum. Okay? Same thing goes with having a derivative of 0. It doesn't necessarily mean that the function has an absolute or has a relative extrema at that point, as you can see here in this example. Okay? The derivative at x equals c is going to be 0, but this is not considered a local or maximum or minimum point. So really, we need to clearly have a point where the derivative is equal to 0, but at the same time, we also need to consider whether or not the sign of f prime of x changes. From positive to negative or negative to positive. if this holds true, then we will definitely have a local or relative extrema at x equals c. So you can see in this example here, the derivatives or the tangent line slopes are all going to be negative on this side and then positive on this side and 0 at x equals c. That's how we have a local minimum. Okay, here derivatives are positive, then negative, then positive. Okay, and then where they change the signs at those points x equals c and x equals d, the derivative is equal to 0. That's how we know we have local extrema. Okay, here in this example, the sign never changes. The derivative is always negative. Okay, and same thing with the infinite slope point. The derivative is always positive. That's why these two, even though their f prime of c equals 0 or f prime of c does not exist, they are not considered local extrema points. So let's move on to page 6. So the algorithm for finding extreme values for a function f of x that has a derivative at every point in a closed interval a to b, the maximum or minimum values can be found by using the following procedures. First of all, you figure out the derivative of the function and then find all of the points in this closed interval where the derivative is equal to 0 or the derivative does not exist. And then what we want to do is evaluate the function at the endpoints a and b, as well as the points where the derivative equals 0 or the derivative does not exist. Then we compare all of the y values that we found. The largest of those values would be the maximum value, and then the smallest would be the minimum value. Okay, so again, keep in mind the absolute max or min value of a function over an interval occurs at one of the following. So where f prime of x equals 0 and it has to change sign. So changing signs from positive to negative or negative to positive, doesn't matter. And it could, again, exist where the derivative does not exist. And that would be the examples of the corner or cusp points. And then a local max or min occurs where f prime of x is equal to 0 or f prime of x does not exist. But remember, we can't say endpoints are relative extrema. Okay? And again, f prime of x must change sign from positive to negative or negative to positive. So let's go over this example 1 here. Determine an absolute extrema or absolute extrema for the following function and the given interval. So this is the function g of t. So our first step in the algorithm was to figure out what the derivative is equal to. 6t squared plus 6t minus 12. And then we said that we have to figure out all the points where the derivative is equal to 0 or the derivative does not exist. Well, we can clearly see that this is a continuous function, so the derivative should exist at all points. So we're just going to set g of t, g prime of t equal to 0. So this is our step number 2. 6t squared plus 6t minus 12. We can factor out a 6. And we can factor this into 6 times t plus 2 times t minus 1. So all of a sudden, we have 2 critical points. So our next step is going to be to evaluate our function value at the critical points, as well as these two endpoint values. So we want to figure out g of -4, g of 2, those are our two endpoints up here. And we also want to figure out g of -2 and g of 1, because those were our critical points. Okay, so it turns out that g of -4, when you plug this -4 into 2t cubed plus 3t squared minus 12t plus 4, we should end up with 24. Nope, sorry, -28, looking at the wrong solution. Okay, repeat this process for g of 2. So again, plug in x or t equals 2 into 2t cubed plus 3t squared minus 12t plus 4. And then we should end up with the y value of 8. Okay, two more times, g of -2 and g of 1. G of -2 will give us a y value of 24, and g of 1 will give us a y value of -3. So one more time, I subbed in these x values into my g of t function. Okay. So now we need to figure out the absolute maximum and absolute minimum. That's pretty easy to do. All we need to do is look for the highest point and the lowest point. So that would be our 24 absolute maximum and -28 absolute minimum. So we want to figure out if these 2 points, the 2 remaining values, are anything of importance. Okay. If you notice, this g of 2 equals 8. This is an endpoint. Okay, so endpoints we said cannot be relative extrema. Just keep that in mind. And if you wanted to figure out whether or not this g of 1 point, g of 1 equals -3, is a significant point, as in is it a relative maximum or a relative minimum, we would need to check to see if the function changes signs at x equals 1. And remember, the way that we check signs is to use an interval table or a numbered line. All right, let's move on to page 7. I would suggest that because I've already gone over an example with you, you might want to pause the video and just work on examples 2 and examples 3 on your own before you press play and check over your solutions. Okay, so I'm going to go over again the algorithm. Here's my closed interval, and first thing I need to do is figure out my g prime of t. So that's going to be 6t squared plus 6t minus 12. If you notice, this is the same function as on the previous page. It's just that I gave you a different interval. So you need to set it to 0. And we already figured out that in factored form, it'd be 6 times t plus 2, t minus 1. Okay? And then our critical points that we figure out would be t equals -2 and t equals 1. However, we cannot include t equals -2 because it is not contained in the interval given to us. Okay? The x values have to be between 0 and 2, right? So because of that, we completely ignore this critical point of t equals -2. So we can only consider t equals 1 and t equals 0 and t equals 2. So g of 0 would be 4, g of 2 would give us 8, and then g of 1, 2 plus 3 minus 12 plus 4 would give us -3. So when we take a look at these values, we can see that we will have an absolute maximum of 8 at x equals 2. We will have an absolute minimum of -3 at x equals 1. And when we consider this point, we know automatically that it can't be a relative extrema because it's an endpoint. Okay. So again, I would strongly suggest that you pause the video and you try example 3 on your own before you check the solution. But here I go. So now I have this function that is a combination, excuse me, product rule. So we need to actually use product rule to figure out our derivative. So derivative of 3y is just 3, and I will leave the y plus 4 to the 2/3 alone. Then I'm going to have to add this to 3y, leave it alone, and then multiply it by the derivative of y plus 4 to the 2/3. And we're going to have to use chain rule here, so I bring down the 2/3 exponent, I leave y plus 4 as is, and my new exponent is going to be 2/3 minus 1, which is -1/3. And then I'm going to have to multiply by the derivative of y plus 4, which is 1. Okay, so let's evaluate. I see that these 3's will cancel out. So I have 3y plus 4 to the 2/3 plus 2y over y plus 4 to the 1/3. Okay, I want the common denominator of y plus 4 to the 1/3. So I'm going to multiply this by y plus 4 to the 1/3. And when I multiply 2/3 plus 1/3, I have to add the exponents. So that's really going to be 1. So it's 3 times y plus 4 and then plus 2y. This 2y doesn't get changed. So then my overall answer is going to be 5y plus 12 over cube root of y plus 4. This is the derivative. And just to mention, the original function, I know that this is continuous because there are absolutely no restrictions on the values of y. Y can be any real number because you can obviously multiply 3 times any value. That's not a problem. And here, this exponent of 2/3, you can take the cube root of any number, positive or negative, you will get a real number back. And then you can square that answer to get another real number back. Okay, so I should just mention that. Y is continuous. Y belongs to the set of real numbers, okay, for the domain. Okay, So that's my first step to figure out the derivative. My second step is to figure out any critical points that I have. And to figure out any critical points, I need to set my derivative equal to 0. That's one way. Okay. And the only way that this function will equal 0 is if 5y plus 12 equals 0. So really, for a function, or for a derivative function even, that when we want to figure out the critical points, the first thing we do is check when the numerator can equal 0. Okay, so this is really looking for the zeros of the numerator. So my one critical point is negative 12 over 5. Now, my second critical point type, if you remember, is when the derivative does not exist. And that happens when the cube root of y plus 4 is equal to 0. So this time, we would be looking for the 0 of the denominator. Right? Because if the denominator of a function is 0, then the overall function becomes undefined, which means that it doesn't exist. So cube root of y plus 4 equals 0. You can cube both sides, so y plus 4 would still be 0 to the exponent of 3, which is 0. And then you get y equals negative 4. This is your second critical point. Okay, so one more time. This is because we wanted to figure out where the derivative does not exist. So we were looking at the 0 of the denominator. And then the derivative is equal to 0 when we're looking at the 0 of the numerator. And this is all about going back to the derivative equation. Okay. Once we have our critical points, we have these two y values to check, and we have the two endpoints of negative 5 and negative 1 to check as well. So that's going to be our step number 3. So we need to figure out what q of negative 5 equals, what q of negative 1 equals, what q of negative 12 over 5 equals, and what q of negative 4 equals. Okay, so put those into your calculators, evaluate. You should end up with these answers. Q of negative 5 is equal to negative 15. Q of negative 1 is approximately equal to negative 6.24. Negative 12 over 5, when y equals that, the q value is approximately negative 9.85. And when q is equal to negative 4, we have q equaling 0. Okay. So that means that we can say, therefore, the absolute maximum value is 0 at x equals negative 4, and the absolute minimum is negative 15 at x equals negative 5. That's it. Okay, let's move on to the last practice question on page 8. All right, example 4. Again, you might want to pause the video and just try this on your own first. The function c of t equals 0.2t over t plus 4 squared models the concentration in milligrams per cubic centimeter of a drug in the blood t hours after it is taken. Determine the maximum concentration when t is between 1 and 8 inclusive. So again, for any sort of max or min value questions now, you need to, first of all, figure out the derivative. So we are going to take c prime t equals, if you want to rewrite this as product rule using the negative exponent, you can. Otherwise, you can just keep it in quotient rule form and just use the quotient rule. Sorry, rational form, and use the quotient rule. So derivative of the numerator is 0.2. Leave the denominator alone. Subtract 0.2t and take the derivative of the denominator, which is 2t plus 4 to the exponent of 1 times 1, chain rule, divided by t plus 4 to the exponent of squared would be the exponent of 4. Okay, so I can see that I have a t plus 4 in common to both of the numerator terms, so I'm going to factor that out. And then I will be left with 0.2 times t plus 4 minus 0.2t times 2 is going to be 0.4t, and then the times 1, obviously. So divided by t plus 4 to the exponent of 4. So I have a t plus 4 here, and I have a t plus 4 to the exponent of 4 here, so I can cancel, okay, and I will end up with 0.2t minus 0.4t, so that's negative 0.2t, and then plus 0.8 over t plus 4 to the exponent of 3. My next step is to figure out my critical points. So that means that I have to set c prime t equals 0, and that's going to be when the numerator is equal to 0. So then when I solve for t, I end up with 0.8 over 0.2, which is 4. This is still within my closed interval, so I'm going to leave that alone for now. I'm going to have to check it afterwards. And I also need to determine when c prime t does not exist. But obviously, this is not going to be an issue because this is when time is negative 4, and that's not in the interval at all. So then that leaves me with 3 points to check. I need to figure out c of 1, c of 8, those are my endpoints, and c of 4, my critical point. Okay, so just plug in 1, 8, and 4 into the original function, get back the y value, and this would be 0.008, 0.0111, and c of 4 is 0.0125. So we can see that the maximum is going to occur at c equals 4. So we can say, therefore, the maximum concentration is, says milligrams per cubic centimeter, so those are my units, 0.0125 milligrams per cubic centimeters at t equals 4 hours after the drug is taken. So that's it, folks. That's it for maximum and minimum values on an interval. So get started on pages 8 and 9 practice and any of the homework that's listed on the unit outline.